Hello, in this video we'll talk about universal gates. We'll first start talking about De Morgan's law and other Boolean properties, and then move to universal gates and define them. And finally, design the basic logic gates using the universal gates. There are two universal gates, the NAND and the NOR gates, and their definition states that these are the gates that can be used to implement or to build other gates. So using the NAND gate only, we can implement all other logic gates. We can also use the NOR gates only to implement the other gates. We'll see how we can do that in the future slides. So let's start with the NAND gate. The NAND gate is short for not AND, meaning it's an AND gate with an inverter connected at the output, if you want to think about it logically. So it is the inverse of the AND gate. And remember, we said that the bubble at the end or at the output represents the inverse or the inverter. The first property we'll focus on is the inverter property. We know that if you have two inverters connected in cascade mode, like what you see here, then the input is A. Then the input is the output of the first inverter is A bar. The output of the second inverter is A, because we know that A bar bar is equal to A. So any variable inverted twice is equal to itself. So this is the simplification of or one of the Boolean properties, you can say, is that A bar bar is equal to A. Complementing a variable twice results in the same variable, the original variable. Okay, now let's start implementing or understand how we can implement the inverter gate using the NAND gates only. We'll do that algebraically, so or verify it or prove it algebraically. We can say that A is equal to A and A. This is one of the Boolean properties. So ANDing a variable with itself or a signal with itself results in the same signal. Okay. Then if we complement both sides, we'll get A NAND A is equal to A bar. So this solves how we can implement an inverter or a NOT gate using NAND gates only. So we can sketch this as a NAND gate whose inputs are shorted or connected together, and the input, we can name it whatever we want. It could be A, thus the output is A NAND A, which is equal to A bar. So this is an inverter made using NAND gates only. Now we will move on to understanding how we can implement the AND gate using NAND gates only. We'll start first by expressing the AND gate as a Boolean expression. We will say y is equal to A and B, and this is equivalent to A and B bar bar because of the first rule we introduced today, which is A bar bar is equal to A. So we're just applying this to A and B together. Okay. Then if you notice here, the bottom half of the expression is actually NAND gate, and then the top half is an inverter. But we already learned how we can design an inverter using NAND gates only. So we can sketch this as A NAND B with an inverter here connected using NAND gates only. So the result is A and B. So we need two NAND gates to create an AND gate. Next, we will aim to implement the OR gate using NAND gates only. We'll start by writing the expression for the OR gate as y is equal to A or B. Next, what we'll do is complement this twice and say that this is equivalent to A or B complemented twice. Now what we can do is apply De Morgan's law, which states that A or B bar is equivalent to A bar and B bar. Okay, so we'll apply this law, which is De Morgan's law, on the following expression. which will result in having A bar ANDed with B bar with a bar on top. So this is actually not A, NANDed with not B. And we already know how to implement the NOT gate using NAND gates only. So we're going to start directly sketching the expression. So we'll have two NAND gates for the inversion of A and B, and then one NAND gate to perform the top complement. So the expression is not A NANDed with not B. This gives us A or B according to De Morgan's law. Now we're going to explain how we can use the NOR gate, which is the second universal gate, to implement the other basic logic gates. Let's start with the inverter. So we can express the inverter as y is equal to A bar. For the verification or the proof of how to design an inverter using NOR gates only, we're going to start by writing A as A or A, which is close to the NOR gate. We're getting closer. So the next step is to complement both sides. So you can say that A NOR A is equal to A bar. Now we can simply sketch the expression using one NOR gate whose both inputs are connected together and labeled as A, and the output is A NOR A, which is equivalent to A bar. So now this is an inverter made using NOR gates only. We only needed one NOR gate for implementing the inverter. Next, we will implement the OR gate using NOR gates only. We'll start by writing the Boolean expression for the OR gate as y is equal to A or B. And then we will complement this twice, so it is equivalent to itself. We'll say that this is equal to A NOR B inverted, so the complement of A NOR B. All right. The top complement is simply an inverter, and we already know how to implement an inverter using NOR gates only, and the bottom complement is just part of the NOR gate. So we can sketch this directly as two NOR gates connected like that. So the first NOR gate performs A NOR B, the second NOR gate complements A NOR B to obtain A or B back. Now we're going to move on to how to implement the AND gate using NOR gates only. We'll start by expressing y as A and B. Next, we're going to complement this twice, so it is equivalent to itself. We're going to say A and B complemented twice. The next step is to distribute the bottom complement using De Morgan's law. So this will convert the expression into something closer to the NOR gate. It will give us A bar NOR B bar. We already know how to create A bar and B bar using NOR gates, and the last NOR gate is just a direct NOR gate. So we can sketch this directly. It will be a total of three NOR gates. The first NOR gate is to calculate A bar. The second NOR gate is to calculate B bar. The last NOR gate is to find A bar NOR B bar, which is equivalent to A and B if you apply De Morgan's law. The last gate we will implement is the XOR gate, or the exclusive OR gate. This slide is just to refresh your memory on what the gate does. Basically, it outputs a 1 when you have an odd number of 1s at the input. Or for the case of the two-input XOR gate, the output is 1 when only one of the inputs is 1. Okay, and you have the truth table of it. Next, we will aim to implement the XOR gate using the universal gates, and we will verify the truth table with the truth table of the XOR gate. So we'll have this as a reference to check our answer if we simulate the logism. Now what we'll do is create an XOR gate using NAND gates only. We'll do this algebraically. We can do it using the expression itself after we sketch it using AND or inverter, and then replace each gate with its NAND gates representation. But for this exercise, we will do it algebraically. So we're gonna start by writing the fact that A XOR B is actually just not A AND with B, ORed with A and not B. So this proof only explains that Y is equal to A XOR B, and then from the first line to the next line, we're just expressing it using AND gates, OR gates, and inverters. The third line simply adds zeros to the expression, or ORs zeros, because A ANDed with A naught is simply 0, B ANDed with B naught is just 0. So we're just ORing 0 to the expression for the purpose of being able to rearrange it and then factoring things out. So B bar is 0, A bar is 0. We're just using them here to help us factoring B out of the first term, like this. So this is our first term here, and we factored out B from it. In the second term, the second half of the term, we're factoring out A. So we're taking A as a common factor and rearrange things. So we're here only applying Boolean properties. Number of Boolean properties that we know, we're applying them to reach the proof of how to implement the NAND gate using how to implement the XOR gate using NAND gates only. So what we did from here to here is factoring out not A or not B. It's here. This results in A or B ANDed with not A or not B. So all of this work is to verify that this is actually A XORed B. We can express it as this. Starting from this last line, we're going to continue with proving how we can implement the XOR gate using NAND gates only. So what we did here is we complemented the second term because it's equivalent to itself. We're applying the rule of A bar is equal to A. Okay, and then from here to here, we applied De Morgan's law. Okay. And then from here to here, we're just distributing this term to both A and B. Again, here we're complementing twice using A bar is equal to A. And then we applied De Morgan's law once again. Okay, now we can observe that the last expression is all written or expressed as NAND gates only. All right, so we can connect this or sketch it to give us how the implementation of the XOR gate using NAND gates only. And this is the final answer or the final result. If you find the truth table of this expression, it should give you exactly the truth table of the XOR gate. So it will be something like A, B, and then Y, or A XOR B, is equal to 0, 0, 0, 0, 1, 1, 1, 0, 1, and finally 1, 1, 0. Something like this. Okay. Now we'll explain how we can design an XOR gate using NOR gates only. We'll start by we'll start from where we stopped earlier with the proof of the XOR gate and how we can simplify it. And then from here we're complementing twice, and then we're applying De Morgan's law, and then from here to here, we're also applying De Morgan's law to the second term. And then from here to here, we are distributing the first term to A and to B. So it's just applying basic Boolean properties to reach the final goal, which is converting all of this into an expression that looks like NOR gates, the NOR gate, A NOR B, or A plus B with a bar on top, something of that form. Now, from here to here, we simply applied De Morgan's law just to get rid of the ANDing in here and transitioning it into ORing. And finally, this looks like an OR. So to make it look like an OR gate instead, we complemented the expression twice. And we already know how to create an inverter using NOR gates only. So the final sketch for the XOR gate made using NOR gates only should look like this. Now, before we proceed, I would like to remind you that any logic function should have the possibility of being expressed using a truth table, logic diagram, as well as a Boolean expression. And these all should be equivalent, meaning if you're given a truth table, you should be able to figure out the expression and the logic diagram. They all should represent the same thing. Okay, this slide summarizes the implementation, or how we can use the universal gates to implement the NOT gate, the OR gate, the AND gate, and the XOR gate, using NAND gates only and using NOR gates only. We can use it to substitute any gate from a logic diagram by its corresponding implementation using NAND gates only or NOR gates only. This way we can use only the universal gates to implement the expression. So here we're going to do an exercise of implementing an expression using NAND gates only. You can do it using two ways. One way is to solve this algebraically, which is what I'm going to do right now. The second method is to sketch the original expression and then substitute each gate in the sketch or in the logic diagram with its corresponding, or with its mapping of the NAND gate representation. So let's start doing the expression algebraically. We can say that F is equal to A, B, or CD. And we know that the NAND gate looks something like this. So A and B with a bar on top. So if we see any or any plus sign, our aim is to apply De Morgan's law so we can get rid of it and convert it into ANDing. So I'm going to start by applying De Morgan's law on this. For me to be able to do that without changing the expression, I'm going to complement it twice. And then say that this is equivalent to A ANDed with B bar ANDed with C NAND D. And there's one more complement on the top. I only distributed the bottom one here. Okay. Now this term looks like it consists of NAND gates only, but the whole term, completely along with A, still uses an AND gate between A and the expression on the right. So what I'm going to do is, again, complement the expression twice. So let me do it here. I'm going to complement twice, and this will result in, I will just rewrite it so it's clear, A bracket B naught and with C D naught, or C NAND D. And there's a bar here, and then two bars on the top. Now I have the expression written in almost just NAND gates only. Okay. Now I'm gonna start sketching it using NAND gates only. I know B bar is an inverter, but I already know that it can be expressed as B bar, I can say that B bar is equal to B NAND B. So this is easy. I'm gonna skip expressing it like that and start sketching the schematic for the circuit. So I'm gonna say we will say B. We want to get B bar, right? So we'll implement an inverter using NAND gates only. So this is B bar. I need to calculate C NAND D or sketch C NAND D. So this is simply just one NAND gate whose inputs are C and D. Okay, all of this term is NANDed together. So I will need one NAND gate here. And then the output of this NAND gate is also NANDed with A. So I'm going to create a new input, name it A, and then NAND the expression here. There is one complement at the end. So it's an inverter made using NAND gates only. So I can just create an inverter using NAND gates only, and then the output is F. The NAND gate takes two inputs, but here it's an inverter made using NAND gates. So I'm going to short the two inputs together, so it will act as an inverter. We have two gates here acting as an inverter, the first one here and the last one. Okay, now this is how to solve it using algebra. The second method we said is to sketch the original expression as it is. So we'll say F, I'm going to sketch it directly, I don't have to rewrite it. So I will start naming the inputs. We have A is ANDed with B or CD. So B ORed with C and D. And the output of the expression is F. So this is the original expression. Now the aim is to replace each NAND gate with the NAND gate implementation of the AND gate. So for this I will need two NAND gates. One is to perform A NAND B, and the other one is to get rid of the bar on top of the inverter. So it will be something like this. Okay, I have another AND gate, so let me also do it now. I will replace it with two NAND gates like this. Here we have an OR gate. We will replace it with three NAND gates because we can use three NAND gates to create an OR gate. The first AND is acting as the first NAND is acting as a complement to complement the expression or the variable. The second NAND is also to complement. The last NAND is to perform the NANDing because here it's like using De Morgan's law. Okay, so the blue is just OR made using NAND. The orange is AND made using NAND. Now what we have is something a little messy, so I will rewrite it or rearrange it. I'm going to use the overlay I am using, just clean it up a little bit. So I'm going to have A connected to two NAND gates like this. And this is F. Okay, the last NAND is acting as an inverter. Okay, I'm done with these now. Here I have three NAND gates, so let me sketch them in a clearer way. The first NAND is an inverter made using NAND. Another NAND gate, another inverter or NAND gate that's acting as an inverter. And there's one more here that is connected to this NAND gate. This NAND gate is connected to V, which is this wire. Okay, the one at the bottom is connected to another NAND gate like this. another NAND gate. Okay, I only did this one right now. There's one last NAND gate that I need to connect that takes C with D. Now the expression on the right is made by just replacing each gate with its representation using NAND gates only. The issue with this method is that it's slow and it will result in having extra gates sometimes, so it's not really simplified. Remember the first law we introduced, which is A bar bar is equal to A. If I was to sketch this using logic diagrams, it will look something like this, as we showed earlier. So there's A, and then this is A bar, and this is A bar bar, which is equal to A. So this is simply equivalent logically to just a wire, right? We can replace all of this with a wire. However, inverters can be also made using NAND gates only, which is the case here. And an inverter made using NAND gates only looks like this. And if we had two inverters connected together that are made using NAND gates only, this is what we're going to have. So we're going to have to replace them with simply a wire, which is the case here. We have these two inverters that are made using NAND gates only. So we can cancel them out and simplify the expression further, like this. And if you notice now, the expression solved on the left here and this one are exactly the same, except they're made using two different approaches. That's all there is. Just keep in mind that whatever expression you do or create using NAND gates only or using NOR gates only, if you simulated the original expression and simulated the NAND gate mapping of the expression, both circuits should give you the exact same truth table. Otherwise, something could be wrong. One or the other. It could be the original circuit or the NAND gate or the NOR gate mapping of it. If you have any questions, just let me know.